This is from the CATS textbook, Chapter 10, number 57, page 303. And it's just a simple rocket problem with an external force. So if I have a rocket here, absolutely spectacular drawing of a rocket. And the question is, what rate does the exhaust need to be shot out the back in order for the rocket to launch? Well, as long as the acceleration of the rocket is some positive number, and I say positive because I'm going to go ahead and make that positive right there. So as long as the acceleration is positive, it's going to be launching upwards. Now, we're looking for the minimum amount of the rate at which the exhaust is shot out the back. And so this is going to be somewhere close to zero. If we're looking for a minimum amount, this is just some tiny number right here. And so this becomes 0 is equal to dmr dt times the velocity of the exhaust with respect to the rocket plus the external force. Now there is an external force in this case because there is a gravitational pull onto the moon here. I know that G is 1.62 meters per second squared. I know that because it's in the problem. They also tell us a couple other bits of information. Mass of the rocket is 9.5 times 10 to the 5th kilograms. And the exhaust velocity, we have to assume that is the velocity of the exhaust with respect to the rocket, is 4.25 times 10 to the 3rd meters per second. I do need to make one extra comment here. They actually, I would consider this sort of a mistype. This is the exhaust speed. Whether it's positive or negative depends upon how we set up our system. And I went ahead and made up positive, and therefore this should be negative since it's a velocity and it's being shot downwards. Because from the rocket's point of view, the exhaust is going down. So my external force is the force due to gravity, which is just mg. It is downward, so that is negative. I also know this is the change in the mass of the rocket with respect to time, and we are asked to find the rate at which the exhaust is being shot out. And so we can sort of do that double negative there. This is equal to the negative change in the mass of the exhaust with respect to time, because, well, we talked about that in the other video. And this is what we were trying to find here. So we are now left with, let's go ahead and bring this over. M, mass of rocket, times the acceleration due to gravity, mass of rocket, equals negative d mass of exhaust with respect to time times the velocity of the exhaust with respect to the rocket. So we have d mass e dt, the change in mass over the change in time, is equal to negative mass of rocket over g over the velocity of the exhaust with respect to the rocket. And so we're left with negative 9.5 times 10 to the 5th kilograms times 1.62 meters per second squared divided by negative 4.25 times 10 to the 3rd meters per second. So we will end up with a positive number because the mass of the exhaust is increasing because you're shooting more mass out. And we end up with 362.1. And the units would be, well, meters cancels out, 1 of the seconds cancels out, and I'm left with kilograms per second, which is what I would expect. So as long as it's shooting out 362.1 kilograms per second, we're good. A couple other notes here is that we are assuming that the acceleration of gravity of the moon is relatively constant. As you know, the farther up you get, the weaker it gets, but then that becomes a far more complicated problem. This now becomes related to time, if we do it that way, or at least position, in which case we eventually have to get it in terms of time, and that is for another day. But anyway, a particular problem.